saying we have two parametrizations already for the ellipse. So the first one comes from simply literally stretching the circle. In this particular case, the way I did it, I stretched the circle with Excel, which one that drawn with Excel, in only one direction. Okay, so remember this. So here it is. As you can see, if we can just get to the formula. So I did not do anything to x. X is to cosine. I didn't do anything to y. Y is still sine. Okay, so 2 cosine, and that stretched the whole thing horizontally. But what's interesting is less than obvious of what's happening is the angle remains the same. We are stretched. It's not that we are distributed. The point is not distributed uniformly through the curve. What is uniform is the angle. Okay, we progress through our curve, so it's the same ellipse. Okay, and then what is uniform about it is this. I drew a line. These are 2 consecutive points plotted by Excel. This one, the angle that changes is the same. So if I move to the next point, it's the same angle. Same angle, and you can, I guess in physics you would have described it as constant angular velocity, which does not necessarily mean constant velocity, the linear regular velocity, right? So which is we can actually see it right here, unless it's a circle. So you can actually, where is it? You can actually see it that the distances are more wider in the middle than on the sides, right? On the sides they are clearly closer to each other than in the middle. Okay, so the speed then is not uniform. So we are moving slower at the ends and faster in the middle on tops. So to left and right slow, and top and bottom fast. Okay, so the speed is not uniform, but the angular velocity is. So we rotate at the same angle at the same period of time. That's because that's how we built it. In the meantime, the most interesting probably place for the ellipse is a motion of the planets, and then the motion is not around the center of their ellipse, but rather around one of its foci, and then yet asymmetric. That creates asymmetry, and that asymmetry also is seen through how the speed is changing. And as you can see, I try to do what Kepler did, and that is to indicate that farther away you are from the sun, the faster you're moving. Hold on a second. The slower you're moving. The slower you're moving. So let me try to make that point maybe like this. Like this. So more points at the end, one end than the other. Okay. So the Kepler's law. Anybody knows Kepler's law? It's about the angles, and it swipes out. You swipe out the same area during the same period of time. Okay, like this. Same area. So that is one of Kepler's laws. Number one is that it is an ellipse in the first place. But I think the second one, is that the area swiped by the Earth from that kind of a curved triangle that starts at the sun and then has 2 consecutive points for the Earth. The area is the same. So naturally, then the farther away you are from the sun, you're moving slower, and so that the angle is smaller, but the area is the same. Okay, so that's totally different story, and you can certainly I might do a simulation later on. same area. Okay, but there is actually the third one that is even simpler. If we go back to the um, implicit equation of the ellipse, is x squared over a squared plus y squared over b squared equal to 1. Okay, so this one is easy to confirm. Once again, how do I get it? I just use trigonometry like this. So this I get it through elimination of parameter. So from having two equations, three variables, I eliminate one of them, and I end up with one equation, two unknowns. Okay, so if I eliminate t, that's what I end up with. So x squared over a squared plus y squared over b squared is equal to 1. So implicit equation. So it is a generalization of the equation for the circle, where a and b are equal to, if they are equal to each other, right? Then you simply multiply it out. So x squared over a squared plus y squared over a squared is equal to 1. It's the same as x squared plus y squared is equal to a squared. Okay, so that's a circle. So and what are those a squared and b squared? They are you can guess what is it? These are the ones. Well, we already know what they are. So this is a, and this is b. Okay, so between negative a and a, horizontally between negative b and b, vertically is where our that's a rectangle where our ellipse is located, and that's how we got it. Remember, we stretched it. So if you stretch a circle between negative 1 and 1, that's what you get. So we have, in other words, in this picture, we have b equal to a is equal to 2 and b is equal to 1. Okay, so no stretch vertically. It still goes up to 1 and no beyond, nothing beyond. So the point is that it gives me the third parameterization of the ellipse if I just solve for y. I cannot solve for y in general, but at least two halves of the curve will be treated separately. So can be treated separately. So upper half will be y equal, what is it? 1 minus x squared over a squared multiplied by b squared. Okay, so that is my equation, right? Yeah. Okay, so explicit equation for the upper half of my ellipse. Okay, and then what is the parameterization? It is parameterized then based on x. So in other words, the parameterization becomes x equal t and y equal that expression over there. So if I wanna, so let me just write it out: 1x squared over a squared times b squared. So that's my parameterization. So for y, we have an equation of y explicitly, and you introduce a new parameter with respect to which is equal to x, which means that the equals, where's the equality? This is it. No, that's not quite right. Like this. So the vertical lines at equal distances from each other, like this. So in other words, we're simply progressing horizontally at the same speed. Whatever happens with y is given by the other formula, but horizontally we're moving at a constant speed. So constant angle at a time for number 1, constant area for the second, for Kepler, and this is constant horizontal progress. So horizontal speed is constant. Okay, so three very different parameterizations, and in fact you can see how they are distributed. We had a picture of parameterization for the last case here somewhere. Let me find it. Not this one, not that one, not this one, no, no. Strange, I remember distinctly I had it. Well, I guess this will do. This will do, even though these are not the curve, but the bars. But you can see how you have a lot of bars at the top, and you have very few bars on the left and on the right. Okay, so even though you are moving horizontally at a constant speed. Okay. Okay, so that's the point that I was going to make. What I want to do now is more motion. More examples of motion and how you capture them with parametric curves. And so starting with, once again, Earth is moving around the Sun, but then what? The Moon is moving around the Earth. Right? So that is a complex motion. So it is like two rotational motion at the same time. So even if you assume that the rotation is circular of the Earth around the Sun, and the ellipse. The rotation of the Moon around the Earth is also entirely circular. This combination creates quite a complex picture. So the analogy I could show you, if you so suppose I'm moving my hand left right. Okay, so let's not do rotation, but I'm moving my hand left right, and then there is add a rotation to it. So once again, I'm moving, and at the same time I'm rotating. Okay, so horizontal motion combined with rotational motion. Okay, so that's roughly a simplified version of what happens with the Earth. And the questions are not obvious. They're kind of interesting. For example, does the Earth, as it rotates, it moves forward and it rotates. The way I did it, you can see that the pen actually comes back. So at some point, even though my hand moving forward, but the pen actually moves forward, back, forward, back, forward, back. Okay, so that's a question that you want to ask. Does the Earth do that? Or does the Moon do it? So does it retrogress? That's the question. So the answer is no, but it's not obvious without actually looking at the numbers. And so then we're going to go in a different direction here and pick a similar but more tractable problem, and that is a bicycle. So we have a bicycle, and imagine you've seen it, I'm sure, then in the dark. There is a reflector on the wheel, and if you look from the side, you can see it makes one similar motion like this. Have you seen it? So that's what we're trying to simulate first. So the curve is called the cycloid. And the other two curves that I described have similar names. I think they are all called cycloids, pretty much. The one for the Earth as well, for the Moon, right? That is. So anyway, so we have a bicycle, roughly. Okay, and so there's a reflector. For simplicity, we'll put that reflector right on the edge. Okay, so that's the reflector. Okay, and then it makes a trip. But what kind of trip? It's as you move forward on your bicycle, then you might have once again, the question is, does it retrogress? Okay, or maybe it goes like this. So which one? So it might retrogress or might not. So the fact that the Moon doesn't do it is certainly an interesting question. But here, questions you might ask about, and not only about retrogression, but also which way you are going. For example, if you are that's a calculus problem. If you are riding a bicycle through a puddle, what's going to happen? puddle of water, if anybody had that experience, what happens sometimes? Well, the water flies behind you, and what?
Hits your back.
It hits your back sometimes, yes. Yes. So and you realize that what it means is that this is what's happening. It is going like this. It hits you in the back, so you already has passed it. But the wheel lifts the water from the ground and throw it. But where it is throwing it, it could be throwing it back, or for example, it could be throwing it like this maybe. Okay, so that needs to be figured out, and you do it with calculus and those derivatives. Okay, so to figure out the direction of the tangent line. So just like that piece of dirt or just water attaches itself to the wheel, and then at some point it flies off when it loses the connection, and then where does it go? It goes tangent. Okay, so that needs to be found out. But the first question is these two. Well, first of all, we have to find the equation. So the equation is, or two equations, is derived like this. So we have my circle initially. My reflector is here to begin with. Okay, then I move on with my the circle. The wheel rolls. Okay, well maybe that's not a good place for it. Let me roll a little, like this. Okay, so my yeah, like this. So that's where the new location of my reflector. So the wheel has progressed forward like this. So the progress of the wheel is determined by how far its center went, right? In the meantime, the reflector is doing entirely different things. A thing and might come back or might not. So this is how it has progressed. So let's figure out the equations. We will base on so t is either time or angle. Either way, so we assume that we are rolling at the constant speed, so just as well. T is the n is time or the angle. Starting t equals 0, so t equals 0, and this is after a moment of time we are elsewhere. Okay, so then we need to determine then the coordinates of where that point 0, well 0, 0. Let's say 0, 0 is the initial location, and now we have a new location, and the new location here. So this is it, and the other one is x t y t. And these two are, we need to find these two functions as a function of t. This is vertical. Okay, so we need to know some trigonometry here, and then thinking of t as the angle. Okay, so I forgot the radius r. Radius r of the wheel. So the one thing that we're going to need is compare the two things. The distance that we have covered on one hand, and which is this, and on the other hand this. This. Okay. So the distance that we have covered is the same as the arch of our wheel. You see it right there. The two blue curves. We have one straight line horizontally. It is the blue curve on the piece of my circle visited. Every point corresponds to, it's like this. Like this. So there's a correspondence between a point on the wheel and the point where it was the one touching the ground. Because if it is a perfect circle moving forward, then there's only one point touching the ground at a time. Okay, so then every point on the ground that we have covered corresponds to every point on the wheel on this piece of the curve. Okay, so once this is established, so then the progress is equal to length of the arc. Okay, so from the what is it? Well, let's just say the arc that we're looking at. Okay, so those two are the same. So at this point, we just need to point out what is the put this finger put this sentence in a form that the algebraic form. Okay, so r is the radius, t is time, x, t, y, t are to be determined. So these are the ones that we're gonna now use to represent everything here. So this point is 0r. I'm sorry, yeah, 0r, yeah. So x coordinate is 0, and the y coordinate is r. This one is, the next one is, well, let's say length of the arc. I need a letter for it, say L. Okay, so length of the arc is L. So this point is LR. So the center of the wheel has progressed from 0r to LR. So vertically, certainly no change, and we just moved horizontally from 0 to L. So that's the location of my new center. Okay, so this is R, and this is R, and well, certainly this is R too. But we especially now concentrating on this second circle because now we can determine what that is. And where's my t? Remember, t is also the angle, so this is my t. Okay, so the circle is moving forward by rolling, and why does it roll? As it rolls, it rotates. So that angle it has rotated through is t, and that's exactly what how that radius from the center to our reflector, how much it has turned. So how much has it turned? It is t, right, seen visibly right here. From the vertical to the horizontal, that's the change of t. Okay, so then and then what is judging based on that location, this location? Let me extract that piece of our circle like this, blue. This is our rotation. Okay, this is R, this is R, this is T. Okay, so and this is L. Now this is a trigonometric issue, and I wonder if you remember the relation between the length of the circle, of the piece of the circle, versus the angle. So I want to express L in terms of t. Have any recollection? What if r is equal to 1 at its simplest? So you have a new unit circle, and the angle is t. What is the length of the arc? Everything is in radians. What's the meaning of a radian? This is the meaning of the radian. You measure the angle in terms of the length of the opposite arc. Okay, so that's why this is pi, this is 2 pi. So on one hand it is the angle, pi, 2 pi, and also the length of the circle is 2 pi as well. So that's the idea of a radian measure of angle, right? So based on that, from radian measure, that's why you don't want to do degrees. L is actually equal to RT. So it's certainly proportional to the radius, and then nt simply measures the length, the angle. I'm sorry. Okay. Okay. So with that established, let's go on. and try to find, take a closer look at that rectangle, triangle over here. So what is missing is, x, y, t is that what we need to find. Okay, so this is what I'm looking at. Once again, that triangle over here. So this is, we already know, everything needs to be known here. This is my vertical line. This is, I put angle here. This is r. This is t. So we know what t is. We would rather know what L is. We needed L to know where our new location of our circle is. So this is LR. So we're gonna need that. Otherwise, we know what L is because we know R the radius and we know T how much time has passed. So what is missing is we need to find these coordinates. These are x, y to be found. Well, fortunately, this triangle will solve us the whole problem, right? So let's see. X is. So this is x we're looking for. Okay. This is L. Yes. So this is 0. There, everything started. The location x we know where don't know where it is, but we know that the center is L units from the origin. Okay. So let's find x, and how? Simply x is equal to it will be L minus this distance, right? So this is L, the big one, and then if I subtract the bottom of our triangle, the length of the bottom of the triangle, I'll have my x. And that triangle is what's the length of the orange piece? From the triangle?
It's just L minus X.
No, yes, but no, I'm trying to find x. So I need to express that orange one in terms of the triangle that I'm looking at using t and r. How do we express that? Using trigonometry, we express this orange piece in terms of these two. R sine theta, yeah. R sine t. Okay, R sine t, opposite angle, right? Okay, so that gives us R. Look at it. We have then RT minus R sine t. That's it. So we have x of t as a function now. So the main thing is y, and where is my y? My y is this. This is my y. Okay, so, and what is y? Once again, where's y is, this is r. So what I need to find is this. So it will be r minus this green piece. Right, so the whole thing, yeah, and y, well, this is y. This is y, right? So this is y, this is y. So we take r, the whole height to the center, and subtract that part of the triangle, which is, what is it? R cosine. R cosine t. So, and once again, we are done. The whole equation is here. So together, I have x equal rt minus sine t, and y is r1 minus cosine t. So that is the cycloid. Okay, let me quickly carry out the, let's just plot it rather than, it's probably always a good idea to start with the plotting rather than with any kind of analysis. Okay, so just I think I can use this one. Okay, so this one will be cycloid. Okay, so the formula is there. I will, so where is my x? X is r t minus sine t. Okay, let's say r equal to 1 just to make our life easier. So it will be simply 1 minus sine t, t minus sine t over here. T minus sine t. So t minus sine t. So not cosine sine t, sine t. I think this is right. T minus sine t. Okay, t minus sine t. And for y, it is 1 minus cosine t. Okay, 1 minus cosine t. 1 minus cosine t. Okay, okay, all right. Okay, let's spread it down. See what happens. This is a piece of the cycloid indeed. Okay. A little bit too small, so let me give more value here. More value here. 2 branches, and this is my cycloid as promised. You could what I was seeing here. What we're seeing here is an arch, which otherwise you would say it looks like a parabola. But if you look carefully at what's happening in the very beginning and the very end of this branch, what would you observe? Well, first of all, there is no retrogression, right? So it moves only if your reflector will be moving totally in the forward direction, up and down, but totally in the forward direction, never coming back. But what is interesting is, can you more precisely describe what's happening at that point where it touches the ground?
The limit of the slope's going to infinity.
That's right. That's what it appears to be, and we can confirm that by differentiation. But that does seem to what appears to be. It is vertical, and if you think about it, what's happening is that it is going steeper and steeper and steeper, and then goes vertically, touches the ground, turn on the spot up, and goes up. Okay, so which appears to be an entirely it's quite a turn. So so the question then is it really that dramatic? If you look at the picture more carefully, can you see what? How would you describe? Suppose you are sitting instead of that reflector. It is you sitting on the wheel, right, on the close to the ridge, to the rim, and you are. What are you going to feel when you touch the ground? I mean, once again, you're going down all the way vertical, and then up. All of a sudden, you're going in the opposite direction. What would that feel? Well, look carefully, because you think that it would be like a bump. You bump in a jerk. You think that would be the effect. But if you look closer at the dots, look at the dots. Well, maybe I'll give you a little bit more of them. You see what's happening?
It slows down.
It appears to slow down. That's right. So just examining the parameterization, that suggests already that there is slowing down. So you are going down, vertical down. But if you're really slowing down, once again to be confirmed with calculus, you're slowing in down, and you have a touch, soft touch, and then you slowing down to 0, turn around, and then slowly accelerate. So not only you're not going to feel the bump, you're not going to feel the jerk either. Okay, so we can see it in the beginning. If I really put a smaller number here, we can see what's happening at the very beginning. Okay, see, that is the acceleration is clearly shown by these dots. In the very beginning, you can see how x and especially y, well, x and y, both of them are not changing very fast. And well, you can confirm that with our 2 functions. And never forget that parametric curves, after all, are made of 2 functions. So as you can see, the first function is made of this is how x depends on t, and the second one on the right is how y depends on t. I don't know why it gives me a positive number in the beginning, but it's just probably because of the rescaling of this. Okay, so no retrogression. But if you actually see it, if you ever seen it, that kind of thing as a reflector on the spike or whatever it's called of a bicycle, it does seem to retrogress. So why is that? If you've seen it, the reason is simply it is not located at the edge. So you can actually that analysis can be repeated with placing the reflector every location between the rim and the center, and from the center to the rim and beyond. All of these are possible, and then it is the curve will be the cycloid will vary gradually, and you can imagine where the starting point is. The starting point is in fact when the reflector is placed right on the center. Okay, then there is no up and down; it's just going straight. So this would be the beginning. Then, as you move the reflector towards the rim, it will start to go up and down, but with no retrogression. Okay. Then there's the special situation. Exactly the one that we explored is when it goes like this, touches the ground and then vertically lifts up. Okay. That is the special placement of the reflector on the rim. And it is possible to go beyond the rim, even though it's not going to be a bicycle anymore. But then that's when it will retrogress, just the way I showed you with this, with the pen that I move forward, and that's clearly retrogression, you can see. So you can see how it is, the rotation will be, the motion will be almost entirely rotational, because in relative terms, you will be more rotating than progressing forward. So it will be just like circle, 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 just slightly forward, slightly forward. That's the other alternative at the top. But as you can see, all of them are possible. And that's the same with motion of planets. They also have all of these possibilities, and you don't know what's happening. It all depends on the actual dimensions. So dimension of the distance from the sun to the Earth, and from the Earth to the moon, and then we know the answer. It does not retrogress. In fact, it doesn't even go up and down. It's virtually straight line. Well, kind of. Okay, so I guess I'll stop here, well, so I'll just make sure that you have taken care of the project, but otherwise I'll see you after the break.